We've simplified the computation of derivatives a lot. All we have to do at this point is work out local derivatives, chain them together, and vectorize them to make the implementation efficient. We can go one step further to make our life easier. If we let the computer keep track of our computation graph and provide backwards functions for specific operations, the computer can work out the whole backpropagation algorithm for us. This is called automatic differentiation, or sometimes autograd, and it's the basic functionality of deep learning systems like TensorFlow and PyTorch. Here's the situation we have now. We draw the computation graph on pen and paper, we work out all the derivatives and how to vectorize them, and then we transfer those vectorized expressions to code that we type into the computer. This is what we want to achieve. We specify the operations that we'd like to be able to use. We work out on pen and paper vectorized implementations of their forward functions and backward functions. And then we chain these modules together in a computation graph in our code. The computer keeps the graph in memory and can then use it to automatically work out the backpropagation. This is what we're going to be developing in this last video of the lecture. Now, whenever we work out a gradient, as we did in the previous video, we always look at the node above the one for which we're computing the gradient and use the multivariate chain rule to split the gradient in two. So in this case, we are working out the gradient for W. So we look at the node K in the computation graph, we apply the multivariate chain rule to K, but then the gradient for K is always a value that we've already worked out. We never have to worry about this part of the computation graph and what happens there, because we already have K nabla worked out. And this brings us to the key idea that powers backpropagation and automatic differentiation. Once we have K nabla, we no longer care about anything else that happens above K in our computation graph. That means we can start at the top and work our way downwards. So here's the basic recipe that we're going to work out. We start by defining a computation graph in terms of operations that are chained together. For each operation that takes x as an input and y as an output, if you know the gradient y nabla for the output, you can work out the gradient x nabla for the input. And it doesn't matter what happens outside in the rest of the computation graph, before or after this operation x to y. So in this sense, working out the gradient for this operation is still local, as it was in the first scalar version of the backpropagation algorithm. Now, once you have this knowledge, once you know how to work out the gradient for x given the gradient for y, you can start at the top of the graph and work your way down. This is called backward or reverse mode of automatic differentiation. We start at the output of the graph and work our way back to the inputs. This is efficient if you have one or few output nodes. Note that if we had two output nodes, we'd need to do separate backward passes for each. In the reverse situation, where you have few inputs, it's more efficient to start with the inputs and apply the chain rule forward. This is called forward mode automatic differentiation. Now, since we assumed earlier already that we only have one output node, in our case, the loss, in deep learning, we always use the reverse mode automatic differentiation. To make this idea precise, and to make it applicable to as broad a range of functions as possible, we'll need to set up a few ingredients. The values that we will compute on will be tensors, scalars, vectors, matrices, or their higher dimensional analogs, and we then build computation graphs on these tensors by defining operations with tensors as inputs and tensors as outputs and chaining these operations together. And then once we have this computation graph in place, we can figure out how to work out the backwards functions for these outputs and how to combine all these backwards functions into a pass of the backpropagation algorithm. So let's start with tensors. Tensors are simply a generalization of the idea of vectors and matrices. A vector is a one-dimensional array of numbers, a matrix is a two-dimensional array of numbers, and in exactly the same way, you can define a three-dimensional array of numbers. You can also define a four-dimensional or a five-dimensional array of numbers, but these can be difficult to visualize. We will assume that whatever data we work with, images, text, sounds, will in some way be encoded into one or more tensors before they are fed to our system. Let's look at some practical examples. Starting with a simple classification dataset with numeric features, we can represent this as a matrix for the features, with the instances arranged as rows and the features as columns. And commonly we create a separate vector corresponding for the classification target labels. And since tensors need to contain numbers, we need to encode the target labels, in this case ham and spam, either as integers, as we've done here, or as one-hot vectors. For a more interesting example, we can look at images. These can be represented as 3 tensors. In an RGB image, the color of a single pixel is represented by 3 numeric values between 0 and 1, expressing how red the pixel is, how green the pixel is, and how blue the pixel is. And this tells us that we can represent an RGB image as a stack of 3 color channels, each represented by a matrix capturing all the pixels in the image. And this stack put together forms a 3 tensor. If we have a data set of images, we can represent this as a 4 tensor, with dimensions indexing the instances, their width, their height, and their color channels respectively. At the bottom of this slide, we see a code snippet showing that when you load the CFAR10 image data in Keras, you do indeed get a 4 tensor exactly like this. Next, we need to define operations on these tensors and chain them together into a computation graph. We'll need to be a little bit more precise in our notation than we have been so far when we've been drawing computation graphs. From now on, we'll draw computation graphs with both the operations and the values as nodes. The graph is always bipartite and directed. The tensor node is connected to the ops for which it is an input, and an operation node is connected to the tensor nodes that it produces as outputs. As an example, here is our multilayer perceptron expressed in this new notation. Just as before, it's up to us how granular we make the computation. For instance, we'd wrap the whole computation of the loss in a single operation over here, but we could also separate out the subtraction and the squaring parts of this loss. Now you may note that this graph is not directed or bipartite everywhere, but this is just visual shorthand. Occasionally we will omit the direction of an edge for clarity or omit intermediate nodes when it's clear from context that a tensor node or op node should be there. The actual computation graph we are describing in such cases is still always bipartite and entirely directed. With this computation graph, we hold on to the same assumptions we had before. We have one output node, which has a scalar value, and all gradients that we're going to compute are the gradients of L with respect to the tensors on the tensor nodes. To implement a computation graph, we need 3 classes of objects. The first 2 are shown in this slide. A tensor node object holds the tensor value at that node, and it also holds the gradient of the tensor at that node to be filled in by the backpropagation algorithm. Finally, it holds a pointer to the operation node that produced it, unless this node represents an input, in which case this pointer is null. An op node represents an instance of a particular operation being applied in the computation. It stores the particular op being used, something like multiplication or addition, and the inputs to the op and the outputs to the op. The third class that we need is the one that defines an actual operation. Specifically, a class that tells us, given some inputs, how to compute the outputs. If the difference between an op and an op node is unclear, consider that a single neural network may apply, say, a sigmoid operation many times. The op object for the sigmoid defines how to compute the sigmoid operation and how to compute its gradient. Then, for each place in our computation graph where the sigmoid is applied, we create a separate op node object, which references the inputs and the outputs specific to that application of the sigmoid, together with a single pointer to the op that defines what a sigmoid is and how it should be computed. An op is defined by 2 functions. The function forward computes the outputs given the inputs, just like any function in any programming language. And the function backward takes the gradient for the output, the gradient of the loss with respect to the outputs of our op, and produces the gradient for the inputs. Both functions are also given a context object. This is a data structure, a dictionary, or a list, to which the forward can add any value which it needs to save for the backward. We'll see an example of that later. Note that the backward function does not compute the local derivative as we did in the scalar backpropagation. It computes the accumulated gradient of the loss over the inputs, and it is given the accumulated gradient of the loss over the outputs. So to map this to our linear algebra notation, if we have a function f which takes as its input a and produces b, then the forward function computes that function going from a to b, and the backward of f computes this function, being given the gradient for b and producing the gradient for a. We'll see how to implement these ops later. For now, let's imagine that we have them and see how we can use them to build a backpropagation algorithm. First, we construct a computation graph. More on that later. And once we have this computation graph, computing our model output and our loss and performing the backpropagation becomes almost trivially easy. We simply traverse the tree forwards from the inputs to the loss, calling all the forward functions, and then backwards from the loss to the inputs, calling all the backwards functions. The only thing we need to keep track of is that when we call forward on an opnode's op, all the ancestors of that opnode have been called so that we have all of its inputs. And when we traverse the tree backwards, when we call backward on an opnode's op, that all the descendants have been called so that we have the gradients for all of its outputs. Finally, note this last point here. Some tensor nodes will be the inputs to multiple operation nodes. By the multivariate chain rule, this means that we should sum the gradients they get from all the opnodes they feed into. We can achieve this easily by just initializing the gradients to zeros and adding the gradients we compute to any that are already there. Now all of this assumes that the computation graph is already there. But how do we tell the system what our computation graph should be? It turns out that the nicest way to do this is to describe the computation itself in code, which makes sense. Code is a language explicitly designed for describing computations, so it would be nice to simply describe a computation as a piece of Python code and have the system build a computation graph for us. This can be done through the magic of operator overloading. We simply change what operators like times and plus mean when they are applied to tensor node objects. There are two basic strategies to achieve this: lazy and eager execution. Let's start with lazy execution. Here's one example of what a lazy execution API might look like. We start by creating some tensor nodes, A and B. Now note that when we create these, we don't actually tell the system what values are in them. We just create two objects with room for a value and room for a gradient, but we don't tell the system yet what those values are, and we multiply them together. Now, because in Python we are allowed to change what the times operator means when you apply it to tensor nodes, we can say that the result of multiplying two tensor nodes is another tensor node that we can create on the fly. And while we're creating this tensor node C, we can keep track of how it was created. So for this particular application of the multiplication operator, we are creating an opnode for the multiplication, and we link our resulting tensor node C to that opnode, and we link the opnode to its inputs A and B. All of this happens in the background underwater, and all we see in our code is that we get a new tensor node object C. Now, once we have performed all of our operations, our system has remembered for us the entire computation graph, and all we need to tell it is what the model inputs are and what the loss is. So in this case, let's imagine that this is our whole computation graph, and the inputs are A and B, and the loss is C. And with that information, we can let the system take care of feeding the data to the model, performing the forward, performing the backward, and performing the gradient update step, all in one function. We simply tell the model to start training on this input. Those inputs are fed to the relevant tensor nodes that have been marked as inputs. The system feeds forward through the computation graph, computing the forward computation here by calling this opnode's operation times on these two inputs and producing an output value. That brings us to the end of our computation graph. So now we can start the backwards. The gradient of a node with respect to itself is always 1. And so we can now move backwards back to the opnode. We call the opnodes backward. And the opnode tells us that if this is the gradient for the output, these are the gradients for the inputs. That's called lazy execution. We build our computation graph first, and we decide what the values on the tensor nodes will be later. This has a number of benefits, primarily that we can explicitly compile our computation graph. We can tell the system, now our computation is finished. Now we want you to turn it into a computation graph. And that allows the system to optimize the computation graph to make the computation faster. It's also a little easier to serialize models and a little easier to make training parallel. But the downside is that these kinds of systems are a little difficult to debug. And that's because the line in the code where you're seeing your multiplication is not the point in the code where the multiplication is actually executed, which happens over here. So if there's a bug in your code, you're making the mistake here, but you'll get the error over here. And that mismatch can make it a little bit difficult to debug lazy execution systems. The alternative is eager execution, where we build the computation graph and perform the computation at the same time. Here's what that might look like. Again, like before, we create the tensor nodes, but this time we give them values right away. So as before, we have two objects, each representing a tensor with a value and a gradient, but now the value is set at the moment the tensor node is created. We perform the computation, again, a multiplied by b. As before, we overload the multiplication operator so that our system underwater builds a computation graph, connects the two tensor nodes to an op node, and connects that op node to a tensor node representing the output. But while it's doing that, it's also immediately calling the forward function on the op node and computing the output value for us. So at this point, we have everything we need to call backward on this computation. The system runs the backpropagation algorithm, computing the various gradients, and at this point, these gradients are used for a gradient update step, and the whole computation graph is deleted. Once we have our gradient update steps, we clear the computation graph and we rebuild it from scratch for the next forward pass. This is called eager execution. It's easier to debug because problems in the model occur as the module is executing. We define in our code the multiplication over here, and if something goes wrong in the multiplication, we also get an error for this line in our code. This also allows for more flexible models. In theory, the model can be entirely different from one forward to the next, so long as the parameter tensors are the same. The downside is that this is a little bit more difficult to optimize, and it can be a little bit more difficult to serialize, although in practice the difference will be negligible. This is the approach used in PyTorch, and it's the main approach we'll be focusing on in the rest of this course. So, with all of these algorithms in place, all we have left to figure out is for a given operation with a particular forward function, how do we work out what its backward function should be? We'll look at a few examples. And we'll start with a simple summation operation. This operation takes two tensors a and b as input, sums them together, and produces an output s. This is fed to some downstream computation graph, which may be one operation or many, but at the end, a loss is produced. The forward is simple to implement. We take a and b as inputs, and we simply return a plus b. And now the question we have to answer is, given this forward, what should the backward be? If we are given the gradient for s, the gradient for the output, what should we return as the gradients for a and the gradient for b? The recipe is the same as we saw in the last part. Write out the scalar derivative for a single element, use the multivariate chain rule to sum over the elements of the gradient for the output, and vectorize the result. We'll work it out for a as an example. We start with the scalar derivative for a single element ij. This is defined as the derivative of the loss with respect to ij. The multivariate chain rule tells us to sum over all elements k and l of the output matrix S. And we see here that the first factor within the sum is an element of the matrix S nabla that we are given as the input to the backward function. The second factor we can work out by filling in the definition of S, which is the element KL of the matrix A plus B, and that's simply the element KL of A plus the element KL of B. Of course, the second term disappears, and the first term is only non-zero if I is equal to K and J is equal to L. So we set all the K's equal to I and all the L's equal to J, and we remove the sum. And we see that this derivative over here evaluates to 1, so we are left with simply element Sij of the output. Which means we have a very easy job to vectorize, because the element ij of A nabla is simply the element ij of S nabla, which gives us this result for the vectorization. And by symmetry, we see that the same result should hold for B. So we get this result for the vectorization of B, which gives us a particularly simple implementation for the backward. The nabla for A is the same as the nabla for S, and the nabla for B is the same as the nabla for S. So we simply take the gradient for S that the system gives us, and we return it as the gradient for A, and we return it as the gradient for B. To finish up, We'll show you how to do this for some more operations. You'll be asked to do a few of these in the second homework exercise, so it's important to grasp the principle very well. We'll do the sigmoid function, a row-wise sum function, and an expand function. We start with the sigmoid. The input for a sigmoid is a tensor of any shape for which we implement this function element-wise. Here's what the computation graph looks like. We get some tensor x, feed it to an operation, get an output y, and y is fed through some upstream computation, resulting in a loss. Our goal is to produce x nabla given y nabla. And the recipe we use is to focus on one element of x nabla first, work it out using scalar derivatives, and then to vectorize. We focus on the element ijk, and from the standard application of the chain rule, we see that that is defined by this sum. We fill in the definition of y-abc, which is simply the sigmoid function applied to x-abc, and we see that all terms in this sum are 0 except when a is equal to I, b is equal to j, and c is equal to k. So we replace the a's by i's, the b's by j's, and the c's by k's, and we remove the sum symbol. And then we see that the scalar derivative of the sigmoid function appears here, which we know and we can fill in as the output of the sigmoid times 1 minus the output of the sigmoid. And in our computation graph, the output of the sigmoid is equal to yijk, so we can fill that in. This is our scalar version of what we're interested in. So as before, we can compute our vectorized version of x nabla as y nabla, element-wise multiplied by y, element-wise multiplied by 1 minus y. So this is a pretty simple operation to vectorize, but what it illustrates is that when we want to implement this, we need more than just the gradient for the output of our function. We also need to remember some intermediate values from the forward pass. In this case, the outputs. This is what the context object is for. Anything we add to this context object gets remembered for the forward pass. In this case, we need to remember this value y here, which is called sig x in the code. So we simply add it to the context object, and the system will remember it for us. And when it comes back down the computation graph and calls backwards on this function, it gives us this context object. We read the value y or sig x out of it, and we can implement our vectorized version of the backward. Next up, let's see what happens when we sum out a dimension. We start with a matrix X, and we sum along its rows so that the result which we return is a vector y. As before, we follow the basic recipe, scalar derivatives first. We pick out one element of this matrix, xi, apply the multivariate chain rule, which indexes only in one dimension k, because the output is a vector. We fill in the definition above the line yk, which is the sum over the kth row of x. We can work this sum over L out in front so that we get a sum over k and L, and then we see that we have a factor here that is non-zero only when k is equal to I and L is equal to j. Setting those values equal to each other and removing the sum, we get this. We see that this vector becomes 1, and the result is simply the ith element of the gradient vector for our output. What does this mean for our vectorization? We are essentially looking for a matrix where for every element ij, the value is equal to the ith element of the vector, regardless of what j is. So for the ith row of this matrix x nabla, the entire row should consist of the same value, namely this ith element of the gradient for our output. Or in other words, we simply want to take this column vector I and copy it along the row dimension until the result is the same size as x. In linear algebra, you can get this result by multiplying by a row vector of 1s. And in our code, you can call a function like expand in PyTorch or repeat in NumPy. This is all very straightforward, but we do lose one important piece of information when we're summing out the rows, and that's the column dimension of x. When we return this vector of summed out rows, we lose the information of how many columns x had. So that we need to store in the context element, retrieve by the time of the backward pass, and use it to expand y nabla for the requisite number of columns. In our final example, we'll include a constant argument. We take a scalar and we expand it to a matrix of the given size, filled with the value of that scalar. In the computation graph, that means we have two inputs. One, the value x, and one, the dimension of the output matrix. This dimension is a constant for our computation because it's not a continuous value, so we cannot define a gradient over it. We'll indicate that with a dotted line. That means that the backpropagation algorithm will not try to derive a gradient for this value here. We work out the gradient for x as before by applying the multivariate chain rule over all the elements of y. We fill in the definition of y, which is simply the value x because all elements of y are equal to x. And we note that this factor here is simply 1. So this is the derivative we end up for x. We take the gradient for y and we simply sum it into a single value. Of course, we have two inputs, this size as well. So we need to indicate in some way that we're not returning a gradient for the second input. This can be done in different ways, but in PyTorch you return none for the gradient that is a constant. So with that, we have all the ingredients that we need for our automatic differentiation system. Most deep learning frameworks build on top of these ingredients, adding a lot of things to make our life easier. For instance, there's usually a way of combining model parameters and computation into a single unit, often called a module or a layer. In this picture here, we see a linear module, as it's called in PyTorch, which takes care of implementing the computation of a single layer of a neural network without the activation, and of remembering its weights and its bias. Modules are different from operations in that they only have a forward function, which performs the computation of the layer, but they don't have a backward function. They just chain together some operations, and the backpropagation calls the backwards on these operations. And with that, we complete the picture we wanted to create. A system where all we have to do is to perform some computations on some tensors, just like we would do in NumPy, and all the building of computation graphs and all the backpropagating is handled for us automatically. So long as the forward and backward have been defined for all the operations we want to compute, either by us or as part of a standard library, the system will do the rest. What have we seen? We've looked at neural networks. These were historically inspired by brain structure, but what we see now is that it really boils down to just a pile of differentiable linear algebra. We've shown you the backpropagation algorithm and the way it operates by working out local gradients symbolically and global gradients numerically, working back to front applying the chain rule. For efficiency, we've vectorized this into tensor backpropagation. And then we've shown you how to do automatic differentiation, which allows us to define only the computation of our model and let our deep learning systems take care of the rest. That's all for this lecture. In the next lecture, we'll look at our first special neural network layer, the convolution.